In the paper on biostatistics, we roughly consider 3 topics. So we will spend time more or less equally on 3 topics. The first is survival analysis, the second is clinical trials, and the third is epidemiology. In this module, I'm going to introduce you to the concepts which we shall study in survival analysis and to try and give you some motivation for why this is necessary. We have looked before at generalizations in going from the linear model to the exponential family, and you have seen that when we take this step, it is necessary to develop specific techniques which address this kind of data. In survival analysis 2, we consider a new kind of data, which is censored data. So briefly, we will look at some of the complications introduced by censoring, look at some of the methods, the kind of problems, how to define regression in this setting, and finally, we will also look quickly at a data example motivated by the relatively well-known PBC dataset in R. We will return to each of these concepts in subsequent modules and study them in greater detail. Survival analysis comprises about a third of the paper on biostatistics. So as you can guess somewhat from the name, survival analysis is modeling the time to event in presence of censoring. You can see that there are 3 words in this definition which have been highlighted. The first is the word time. So survival kind of data is necessarily time to the occurrence of some particular event of interest. Now when we say time, we are assuming that we have some well-defined and meaningful starting point from which this time is measured. So for example, if we are looking at the occurrence of disease, this time metric could be the age at which the disease occurs. But also it is not unique and it is not necessary that age should always be the proper metric of time. So for example, if we are considering the occurrence of an occupational disease, say the occurrence of lung cancer in mine workers, then the appropriate time could be time since enrollment in that industry. So when we define survival analysis as the time to an event, we are taking for granted that the fact that we have chosen a meaningful starting point and a meaningful time metric. Now given time, the next highlighted word is event. So typically and traditionally, the event which we consider is death. So typically we are interested in modeling something like the age at death. But again, it is not necessary that this be death. The event could be some kind of illness, or it could in fact be any event of interest. The third word which has been highlighted here is censoring. Censoring means that some of this data could be lost. The reason being that the individuals could be lost to follow-up. There are many types of censoring. So in the simplest situation, for example, the study ends, say, 5 years after initiation, and at that time point, not all individuals have had the disease of interest. So for these individuals, the information that we have is that they have not had the disease in the first 5 years of the study. We do not know, however, whether they do have the disease immediately after the study is concluded. So in this sense, the data is censored. This means that we may or may not observe the event for every individual in the dataset. So again, to summarize, survival analysis is modeling time to event in presence of censoring. Time must be measured using some suitable metric. Event can be any event, any well-defined event of our choice. And censoring can happen in many ways. It means loss to follow-up, and we typically assume that censoring mechanism is independent of the mechanism which governs the occurrence of the event. To understand exactly what this means, we shall have to look at the models and the likelihoods and see what happens when the two become related. What kind of problems do we consider in survival analysis? Well, one very common area where survival analysis is used is clinical trials. This means that we are comparing, for example, survival, that is time to death, for two groups which are on two different kinds of medications. So our objective here is to find some way of quantifying the differences in the survival experience of these groups. More generally, our covariate need not necessarily be one single binary covariate or one single categorical covariate. We could have a continuous covariate, or we could have a mixture of some continuous, some categorical covariates, and we wish to relate the survival time to this set of covariates. However, there are some complications introduced by the nature of the problem. Now note that I have said that survival data relates to time to an event. For a large part of statistical analysis, we assume that the data are normal or under some transformations can be reduced to normality. Survival times, however, are usually non-normal. There is a class of survival models called parametric survival models, and the common models which we use here are the exponential, the Weibull. There is also, however, an equally large class of models which are called semi-parametric models, where we do not make exact assumptions about the parametric form, but loosely some assumptions about the form of the likelihood. The second complication in survival analysis is the occurrence of censoring. Now, as I have said, censoring can occur in many ways. The simplest example could be that the study is terminated, and at the point at which the study is terminated, all individuals have not experienced the event. If an individual experiences the event after the study, then we do not have this information in our dataset. There are many kinds of censoring. So, for example, left censoring, right censoring, interval censoring. But in general, one broad assumption we make about censoring is that censoring is non-informative. This means that if we introduce a random variable for censoring, then the distribution of that random variable does not give me any extra information about the time for event. Now we can see easily that bias is introduced if we ignore censoring. Here is a well-known dataset in the survival library in R. It is called the PBC dataset. There are 4 columns. The first is the ID, the second is the time, the third is the status, and the fourth is the treatment. So treatment is either 1 or 2. The status variable indicates whether or not the person has experienced the event at the point at which the study was terminated, or whether the person was censored. So the time for someone who has experienced the event is the time to event. For someone who is censored due to loss of follow-up or for study termination, it is this last known value of the time at which the event was yet to occur. Now you can get some feel from this data set that bias will be introduced if we ignore censoring. If we look at the status variable, then the value 0 indicates that the corresponding individual was censored. So individual 2 was censored, individual 7 was censored. If we simply ignore the status column in our analysis, then we will assume that individual 2 experienced the event at time 4500, which may or may not be correct, and our resulting inferences may or may not be valid. Let us look at more details of the PBC dataset. The PBC dataset originated from the Mayo Clinic, and it is a dataset on primary biliary cirrhosis of the liver. So the dataset is from a clinical trial conducted at the Mayo Clinic on primary biliary cirrhosis, or PBC, conducted between 1974 and 1984. There are 424 PBC patients in this dataset. Of these, 312 are from a randomized placebo-controlled trial of the drug D-penicillamine. This dataset has been analyzed further in the book by Atanu and Gramsch on extending the Cox model. So here are the covariates which have been included in this dataset: age in years, the serum albumin, alkaline phosphatase, presence of ascites, yes or no, aspartate aminotransferase, serum bilirubin, serum cholesterol, urine copper, edema, whether present successfully treated or present despite treatment, hepatomegaly or enlarged liver, platelet count, blood clotting time, sex, spiders or blood vessel malformations in the skin, the stage of the disease, the histologic stage of the disease, and the triglyceride. In addition to these covariates, we have these outcomes. The first is the censoring variable, which has been defined as status. So status can take values 0, 1, and 2, corresponding to whether or not the subject was censored, had a transplant, or was dead. Time. The time is the number of days between registration into the study and the first of whether death, transplantation, or study analysis took place. The treatment is 1 or 2 or NA, depending on whether the person was included in the clinical trial of D-penicillamine or whether he was not a part of the randomized trial. So what are the kind of questions we might be interested in analyzing in this dataset? The first is we would want to get an idea of the typical survival experience of each patient. So here is a very common name which will come again and again in survival analysis, called the Kaplan-Meier estimator. So in this graph, on the x-axis, we have plotted the survival days, and on the y-axis, something called the survival function, which is the probability of survival up to that number of days. The estimator plotted here is called the Kaplan-Meier estimator, and you can see that it is a stepwise kind of estimator, and that beyond a certain point, which is actually the largest event time, the estimator becomes constant. This estimator is remarkable for many ways. Its motivation comes from something relatively simple, which is the life table, and it can be shown to have quite remarkable statistical properties in that it is the non-parametric maximum likelihood estimate of the survival function. How to derive this estimator, show its properties and its usage is something we will study in later modules. Another very common question could be that we want to compare the survival experience of several groups. So here, for example, it would make sense to compare the survival experience of the two treatment groups. Now here again is the name of a very common procedure called the Mantel-Haenzel procedure, which in fact is a tool for analysis in stratified data situations. To see more about this, you can visit the modules on epidemiology, and to see how we can apply the stratified data analysis tool for survival data, we will look at one module dedicated to the Mantel-Haenzel test. So here is how the Mantel-Haenzel test can be done in R using the survdiff function. I should mention here that just like we create LM objects for studying linear models, LME objects, GLM objects, there is also something called a serve object, and that is what is indicated here by the syntax serve PBC $time, PBC $status equal to 2. We shall look at many more examples of this, and I hope you will be familiarized with the syntax and the concepts at the end of this. So in any case, the summary chi-square given in the last line of this syntax shows that the chi-square was 0.1 with 1 degrees of freedom with a p-value of 0.75, and this indicates that there was no significant difference of the survival experiences of the two groups. So another way to see this could be to plot the Kaplan-Meier estimates for the two groups, and that is what has been done here. So it is interesting to follow this over the survival times, look at the points where they cross each other, and try to interpret this. We can also add confidence intervals and confidence bands around these estimates using estimators like Nelson-Allen, Gehan, etc. And for those two, we will have additional dedicated modules. We are also interested in regression modeling for survival data. So here you can see as part of the syntax the word Cox-PH. Cox-PH refers to Cox's proportional hazards model. It is one of the most common models used in statistics and very commonly used for regression modeling of survival data. The syntax also you can see is similar. So there is a survival object where the first variable is time, the second is sensory, and on the other side of the equation we have the usual regression formula which we have used for LM, LME and many other regression settings and the data. However, the problem here is to make out how to fit the regression model. So note that we are not observing the outcome for a large number of individuals. So we cannot really fit the usual linear regression and plug in any time for these individuals because we do not know the time. There is also the question of deciding how to quantify the associations for this kind of data. Now recall that for a regression problem for continuous outcomes, we were able to do this using regression coefficients. For, say, binary outcome, we could do this, for example, using odds ratios. And we have seen that when we do regression modeling of binary data, it makes sense to estimate the log odds ratios for each covariate. Similarly, it turns out that for regression modeling, we also introduce a new concept called the hazard function, and the coefficients which you can see reported on this slide are in fact the log hazard ratios for each covariate. So what are the log hazard ratios and what do they mean? That is something we will devote not one but several modules for studying in greater detail. So another example which we might be interested in is to find the survival function as a function of the covariates. It turns out that this is not really an easy problem, and in some sense it is necessary to choose between whether we want to relate the survival function to the covariates and the survival function or the survival function to time, and there are many estimators which we need to study in greater detail, like the Nelson-Allen estimator, to get the answer to this question. Finally, after fitting the regression model, there is the question of diagnostics. And again, the concept of a residual is complicated by the fact that we have not observed the outcome for all individuals. So, for example, if we want to define a residual like observed minus expected, so say the analog of the typical y minus y hat which we use in linear regression, we can't immediately do this for survival model because we don't know y for all individuals. So there are ways around this, and just as we have defined several concepts of residuals for the GLM, we can have several different concepts of residuals for survival data. So one of them, which is very common, called the scaled Schoenfeld residuals, is shown in this plot. The idea is similar as for linear models, that when we plot residuals, there should be no pattern, and if there is a pattern in the residual plot, then we need to go back and examine the model which we have fitted. Finally, a part of regression model fitting needs to be devoted to checking the very common assumption of proportional hazards. So I told you earlier that when we model survival data, the natural function to model turns out to be something called the hazard function. Now, roughly the hazard of an event is, at a particular time t, is the chance of that event occurring at time t given that the individual has not experienced the event up to time t. So, for example, the hazard of death at age 50 is the chance of an individual dying at age 50. The hazard of a heart attack at age 60 is the chance of an individual experiencing a heart attack at that age, given that he has not experienced a heart attack before. Now, when we model this hazard function, a very common assumption which is met is that hazards are proportional. This means that if we compare two individuals in terms of their hazard function at a fixed time t, and the covariate values for these two individuals are x1 and x2, then the differences in hazard should always be proportional to the difference in their covariate values. So we can check this perhaps graphically by getting the Kaplan-Meier estimator separately for the two groups, and for example, the assumption of proportional hazards would be ruled out if we can see that these Kaplan-Meier estimators cross. There are some extensions to these common survival models like the Kaplan-Meier model, the Cox model, parametric models, which are at the periphery of the syllabus, and we shall spend some brief time getting an idea of them, though perhaps not explore them in much detail. The first is the frailty model. So the frailty model assumes a subject-specific effect. You have come across subject-specific effect in longitudinal models or in mixed models, in generalized mixed models. Frailty models do the same kind of thing when you have time-to-event data. There is something called a competing risk model. So say we are looking at the time to disease, it is not necessary that the individual has to either experience that particular kind of disease or be healthy. We could instead choose to consider, say, 4 or 5 alternative disease, or perhaps 4 or 5 alternative causes of death, which are in some sense competing. So this is a kind of multivariate data in time-to-event setup. We could also look at multiple events. Now, if we look at an event like death, then obviously this event occurs just once. However, we could look at, say, time to headache since starting a new migraine medication. So this headache can occur many times, and as such, this is like the longitudinal equivalent to survival data analysis. Finally, there is also a class of bivariate or multivariate survival models. These models were initially motivated by some seminal work done by Anderson on modeling disease in the right eye and the left eye. It turns out that the experiences of the two eyes for the same individual is correlated, and in that sense, this is an extension of the idea of correlation to the case where we have a time-to-event outcome. In this module, we have been introduced to the concept of survival analysis. We have seen that survival models are required for the analysis of censored data and that we are looking at data which is time to event. These two characteristics of the data require the development of extra methodology to address these two complications. We can see that ignoring censoring will lead to biased estimates, and we looked at some ways to account for censoring in the model. We looked at some typical models and estimators and procedures which arise in survival analysis, for example, the Kaplan-Meier curve or the Mantel-Haenzel test, checking for proportionality, new kinds of residuals like the Schoenfeld residuals. We also considered an analysis of the PBC dataset in R, and very briefly, we looked at some further models which are in the periphery of this syllabus, but which can arise often while analyzing time to event kind of data.